Yeah, we'll see this question which is asked in 1993 paper. Number of tracks per recording surface is given, which is 200. Remember it. Disk rotation speed is 2400 rotations per minute. Now the track storage capacity is given, which is 62,500 bits. You remember? Now the rotational latency of this device is p milliseconds. So, and of course average rotational latency is p milliseconds and data transfer rate is q bits per second. We have to identify p value and q value. That means I want to find out average rotational latency, second one data transfer rate. So what is the average rotational latency? I will tell you. This is your plate. Okay, so this is, let's say, your track, and this is the current sector which you want to read. Okay, this is the data you want to read. Now initially this read write head will be located on the appropriate track, correct? Now if your fate is good, then the track will directly go to the data. But sometimes what happens, if your data is far away from this read write head's pointer, then probably we have to rotate the plate. We know that, right? So we have to rotate the plate so that the sector will come to, the data sector will come to the right place. That means it should come to the read write head. How much time it will take? So that is nothing but exact rotational latency. But we cannot find out exact rotational latency because it depends on the distance between this data and your pointer. So the distance between this pointer and data is highly variable. It may be 0 if already the sector is on, your read write head is under this, on top of this data. In the worst case, maybe it is here, so that complete rotation is required. We have to completely rotate the plate to get it right. Easily we can understand these, distances and all, right? Easily you can understand that. In the worst case, it will take one rotational latency. That's what people realized. Since it is variable between 0 to 1 rotational latency, anything can happen. Then using some probability, so I am assuming that every case is equally likely, then average case will become half of, because values are 0 to 1 rotational latency, then we can say average as half rotational latency. From now onwards, because exact calculation we cannot do, then the rotational latency we take, that means average rotational latency will take as half of the rotational latency. Sir, what is one rotational latency? How to calculate it? We will see. We will see exactly one rotational latency. One rotational latency is nothing but the time required to the time required for a disk to rotate exactly one, complete one iteration. We will see that. We have given, this rotation speed. What is that? 2400 rotations per minute. So we'll ask directly that speed. My dear, disk rotation speed, what does it mean? What is 2400 means? That means within 1 minute the disk can rotate 2400 times. That means 2400 rotations per minute. Minute means 60 seconds. But I would like to find out one rotational delay, correct? So that's why one rotation takes how much time? That would be, see, remember one thing, this is direct proportionate, correct? 2400 60 seconds, one rotation also depends on the number of rotations. That means, so for 2400 rotations 60 seconds, for one rotation it will be less, correct? So that's why among these two, which one is less? One will be on nominator, 2400 will be denominator. See, generally in my childhood I have learned this trick. What is that? Is whenever you have this kind of question, 2400 rotation 60 seconds, one rotation how much, then you ask this question to these values. For 2400 rotations, if it takes 60 seconds, for one rotation it takes how much time? Lesser than the this value. That means lesser than or more than this value? Definitely lesser, correct? Because it will be, for 2400 it is 60, for one definitely it is lesser than 60 seconds. Then in these two, which one is least? One will come on top, 2400 will come down. If you get the keyword most in when you are asking this question, if the keyword is like this, 2400 rotation 60 seconds, one rotation takes more than 60 seconds, then more means among these two, which one is highest? 2400 will come on top, one will come on bottom. That is the way. So generally you can remember this kind of formula, 1 by 2400 into 60 seconds, right? So 60 40 is it would be 1 by 40 seconds. That is nothing but 1000 milliseconds is nothing but 1 second. Remember, I am converting 1 second into 1000 millisecond by 40. Then if you simplify it, you get 25 millisecond, remember it. Finally, one rotational latency is 25 millisecond, but we would like to find out half of the rotational latency because average is half, right? So half of the 25, which is nothing but 12.5 millisecond. From now onwards, whenever the question is about average rotational latency, simply the formula is half of the full rotational latency, which is nothing but half of the 25 here, which is 12.5 milliseconds, remember it. Now, the second question is data transfer rate. So how to understand data transfer rate, I will tell you. This is your disk. Okay, data transfer rate comes into the picture after locating the data. So assume that let's say your read write head comes to the right place, so the data is already available. Okay, so after that, how much time further you require to transfer the data? So it depends, most of the times it depends on the speed of the disk, right? In the problem they have given only speed of the disk, right? No other parameters. Then using this we can solve this problem like this. See, if only this disk rotation speed limits us, then one in what is the rotational speed for one rotation? How much time it will take? So one rotation takes, already we have seen 25 millisecond, correct? So that means what? So within 25 millisecond of time your disk will be completely rotated. See, whenever you want to take the data, first of all disk has to be rotated, correct? See, this is your read write head. While rotating we are taking the data, then how fast that rotation can take place? With the same speed we can take the data. That is what the idea. Okay, so since within 25 millisecond it can completely rotate, if it completely rotates, then entire track I can read. So what is the track capacity? That's why track capacity is important. The track storage capacity is 62,500 bits. Now I can say like this: to read 62,500 bits, okay, this disk has to be rotated for one full rotation. So one full rotation time is 25 millisecond. So this is the your data transfer speed, right? So 62,500 per 25 millisecond. Then for 1 second, how many bits we can take, right? So if you simplify it, you might get this answer like this. So again same question, for 25 millisecond 62,500 bits, but I have 1 second means what? A bigger number, right? 1000 milliseconds. Within 1000 milliseconds, how many bits you can transfer? More. So in these two, which one is more? 1000. That's why 1000 will come on top, 25 will come on bottom into 62,500 bits. Let us simplify it. 25 4s 100, it would be 40, right? So 40 into 62,500 bits per second. This is the speed. Okay, the question is also q bits per second, then q is nothing but 40 into 62,500. You can simplify it. See this question which is asked in GATE 2001 paper. Okay, 20 surfaces, 1000 tracks per surface, 16 sectors per track is a configuration of your disk, and data density is 1 KB per sector. Okay, fine. And rotation speed is given as 3000 rotations per minute. Now we'll see the remaining data. The operating system initiates the transfer between the disk and the memory sector, sector wise. What he's saying is, so this is your secondary memory, let's say. This is your primary memory. Then whenever the sectors are transferred from this secondary disk to main memory by initiation of operating system. Yes, usually that is a way. So that is what he clearly mentions. What is that? Operating system initiates the transfer between the disk and the memory sector wise. So every sector will be taken and transferred. And remaining details, if you see, the disk reads a sector. Before that, you see, once the head has been placed on the right track, we know one thing, right? So your disk will be imagined as plates, right? When you come to the right plate, so once the head has been placed on the right track, here he has already mentioned that, let's say the track, I mean your read write head is on the right track, then the disk reads. He is explaining how disk will be read. Once the this IO head is kept on the right track, the disk reads a sector in a single scan. So let's say this is your sector and this sector will be read in a single scan. Fine. It reads bits from See, sir, but we have to rotate the plate, right? Yes, that's why rotational latency is given, don't worry. So once the sector is so whenever your read write head is on top of this sector, then data will be read. How you see? It reads bits. That means the circuitry reads bits from the sector while the head is passing over the sector. So when because plate is getting rotated, right, then slowly every point or every bit will go through this read write head. While it is going through read write head, then data will be read, and every bit will be understood, and that bits will be converted into bytes. Read it, you understand? It reads bits from the sector while the head is passing over the sector. The read bits are formed into bytes in a serial in and parallel out buffer. There is a buffer. So whenever you are reading the bits, they will be grouped as bytes and they will be transferred to this buffer. And each byte is then transferred to memory. Once you form these bytes, then each byte will be transferred to your main memory. So that's why main memory access time is given, you see. The disk writing is exactly, and one more thing, the disk writing is exactly complementary process. Okay, we understood that one. That means writing is also same way. Now assume memory read time. If you want to read the memory, it takes 0.1 microseconds. That means whenever you want to consult a memory location, main memory location, it takes 0.1 microseconds. You have to remember it per a byte. So interrupt driven transfer has an interrupt overhead 0.4 microseconds. That means question might relate the problem to interrupt driven transfers. Second one, DMA initialization also given. DMA initialization and termination overhead is negligible. That means don't consider initializing the DMA and termination in the DMA. So DMA requests are always granted. That means whenever DMA request happens, that will be automatically granted. Remember it. Now the question number 1 is, what is the disk capacity? Okay. So what is the disk capacity? We will see. How to find out the disk capacity? It's very easy. First, that depends on the number of surfaces. How many surfaces we have? 20 surfaces, right? Then first find out each surface capacity. Then multiply it with 20 because we have 20 surfaces. If you find out each surface capacity, then the answer will be 20 times of the one surface capacity. But what is the surface capacity? That's why here I am going to compute surface capacity. What is surface capacity? If you want to understand, you should understand the number of tracks in that surface, correct? So the number of tracks are 1000. So that's why surface capacity is nothing but 1000 track capacity. If 1000 tracks take some x bytes, then surface also takes x bytes because we write data on tracks. How many tracks we have? 1000 tracks. So finally problem is reduced to 20 into 1000 tracks. These many tracks we have overall, but what is track capacity? If you want to know the track capacity, track has 16 sectors. So if you want to know one track size, you simply multiply it with 16 sectors. Correct? So now finally problem is reduced to sectors. 20 surfaces, each surface has 1000 tracks, each track has 16 sectors. So these many sectors we have. But I want to know the answer in bytes. Then I should know what is the sector capacity. So data density per a sector is 1 KB. So sector can be removed and we can write 1 KB. 20 into 1000 into 60 into 1 KB. So this will be your final disk capacity. Simplify it, it would become, see, 2 16s are 32. Then remaining are 10 to the power of 4 into K means 10 cube bytes. So finally these many bytes. Let us simplify further. 32 into 10 power 7 bytes. Correct? So this is the capacity. Now we'll see the second question, that is data transfer rate. So we know how to find out data transfer rate. It depends on the time required for rotation, right? So we will see 3000 rotations per minute. So I can say that for one rotation it would be, we have seen the formula already, 300 rotations per minute. Minute means 60 seconds. So for one rotation how much time? It would be 1 by 3000 into 60 seconds, right? So this is for one rotation. Now in this much time, let us calculate this value first. 0, 0, then it would be 1 by 50, correct? 1 by 50 second. If you convert it into millisecond, it would be 20 milliseconds. That means within 20 millisecond we can complete track we can transfer. So with that we can find out the data transfer rate. So data transfer rate is nothing but for 20 milliseconds one track. What is track capacity? In a track we have 16 sectors. So each sector has 1 KB data, right? 16 into 1 KB, 16 KB. Now your disk can transfer the data 16 KB in a 20 millisecond. Let us do again like this. 20 milliseconds 16 KB data, but I would like to know the capacity per 1 second, right? 1 second. Then more data will be transferred. That's why it would be 1 by 20 milliseconds, right? So let we do one thing. Remember one thing, always it would be better to have all the parameters or all the measurements uniformly. That means you have here milliseconds, here you have 1 second. So what is my suggestion? Always better have uniform measurements like 1000 milliseconds. So 1000 millisecond, how much? Then answer will be 1000 by milliseconds by 20 millisecond into 16 KB. So all about aptitude. Seconds will be cancelled, milli will be cancelled, 00 will be cancelled. It would be 2 by 100 by 250, 50 into 60, 8000, right? 1600 by 2, 800 KB. So this is the per second. So in that way, we can easily find out the data transfer rate, 800 KB per second. See this question, see, percentage of time CPU is required for disk IO for byte-wise interrupt-driven transfer. So generally we don't do interrupt driven transfer for disks, we do direct memory access, but it's a hypothetical question. That means they are exploring the possibility of sending the data from disk to main memory through interrupt driven model. Okay, so we should just understand what are the things required in interrupt driven transfer. First of all, this is your CPU and this is your memory and this is your disk. Since it is interrupt driven IO and in the question they have mentioned how to take the data, correct? So we will go to the right plate and right sector. After that we start transferring the data bits wise, right? So every bit will be taken one by one, one by one, one by one, and we form a byte. Then we group it as a byte, correct? Once byte is prepared, then we will generate. So that is what the story of disk. This is the way data is formed, right? So we will go to the right data and every bit will be collected and we form the bytes. Now let us mix this question, this concept with interrupt driven transfer. In interrupt driven transfer, once byte is prepared, then we have to stop the process and we have to create an interrupt. Otherwise we have to generate an interrupt. Okay, this is your CPU. My dear CPU, I got the byte number 1. Now this is your turn to continue. Then CPU will execute the corresponding interrupt service routine so that data will be transferred from byte to this place, right? Maybe that interrupt service routine will have typical instructions like store, assume that this is register R1, store, okay, disk register, let's say DR1, just for easy understanding, that's it. Store the value which is DR1 into a main memory called something X. So in that way, that X is also mentioned by this disk controller, right? So this kind of instructions are part of interrupt service routine. Now, and how much time they take? So it is given that 0.4 microseconds, 0.4 microseconds they take to send the data from here to here using the interrupt service routine, and I explained some instructions in it, correct? Now after that what are we going to do? What we are going to do is we take another byte. Once it is done, CPU simply disables that interrupt, then again the remaining work will be done. Again your disk controller will ask that circuit to read the second byte, right? Again your disk will be continuously read, then second byte will be taken, then again same thing we do, right? In that way, once byte is prepared, we call the CPU and CPU will finish the work in that way. That is what interrupt driven IO, right? Now what I want to say is the seek latency is not given in the question because seek latency is not really required. Why? Because when you have large amount of data, see this is, let's say, your large amount of data, right? These are all various bytes in your disk. Then let me focus on a particular track. This is some track number 1. Then the track contains huge data. Then the seek latency is only for the first byte, because recall, first of all IO head will come to the right place, then data will be transferred. For first byte probably you have to come to the right position, but later then remaining bytes are on the same track, then your read write head need not be moved, correct? So that's why we can ignore seek latency, because it is not for every byte, only for the first byte. Similarly, the rotational latency, average rotational latency also we can ignore, because once example, let's say your read write head is somewhere else, then we rotate the plate so that data will come under this read write head, but after that remaining data doesn't require this rotational latency, correct? So that's why for a typical 1 byte, for a random 1 byte, seek latency and rotational latency are average rotational latency are not really required. We don't need to consider them. Then what we have to consider, only the data transfer, because every byte will face this data transfer. In one line, can I say one thing? Seek latency and that average latency which we consider for data transfer are not required, because they are not for every byte. So for every byte, what is compulsory? Transfer time. That's why, so let me focus on only data transfer time. So how much time this byte will take? We will see that. So data transfer time already we know, right? What is that? The data transfer rate of your disk depends on that rotations per minute. With that, already in the question B we have solved it. We got 800 kilobytes per second, right? That is your disk capacity for transferring the data. For 1 byte, how much time it will take? So that would become 1 byte by 800 KB into, that's it, 1, right? 1 second. So this is the answer, which is in seconds. So let me simplify it. Byte gets cancelled, then you get 1 by 800k seconds. Let me convert it into microseconds, okay? Because all other variables are in microseconds. 800k. I can do one thing. I write 10 power 6 into 10 power minus 6 seconds. So that 10 power 6, 10 power minus 6 will be cancelled. Here what I do, 10 power minus 6 second can be written as microsecond. So that means what? 1 second is nothing but 10 power 6 microsecond. Now I use here 800k. Now let me simplify further. It would be 10 to the power of 6 by 800k is nothing but 8 into 100 means 10 square, k means 10 cube, 10 power 5, right? Microseconds. If I simplify it further, 10 by 8. 10 by 8 is nothing but 1.25 microseconds. So finally, data transfer time of that byte is 1.25 microsecond. 1.25 microsecond. Now let me complete the story. If you see, what is happening is, you are transferring a byte, right, repetitively. For any byte, if you see, first of all, we don't disturb the CPU. We simply transfer the data from disk to that temporary buffer. There will be a disk and there will be a buffer, disk buffer I can say. Every device will have a temporary buffer. So we move the data initially from this device to this buffer. For that, this much time it will take, 1.25 microsecond, because it depends on the rotational latency, 1.25 microsecond, right? After that, we generate an interrupt. Because of that, CPU will come and CPU will finish the job. It will transfer the data from this buffer to main memory. It takes 0.4 microseconds. Sir, how do you know that? Because it is clearly mentioned in the question that interrupt overhead is 0.4 microseconds. Now you see, sir, after that it will be repeated for every byte. So now that's why let me focus on only 1 byte, because for every byte, if something is same, then we can only focus on one particular byte. In this byte, that means in this period, what is wastage? Where are you using CPU? Here, 0.4. 0.4 out of 0.4 microsecond plus this is 1.25 microsecond. I can say that 0.4 by 1.65, right? Sorry, 0.40, 1.25. 1 rupee 25 NP, 40 NP, 1 rupee 65 NP. It would be 0.4 by 1.65. This is the fraction, or this is the ratio of the time you are using the CPU, right? If you want to know the percentage of time, then I can say 0.4 by, so 1.65 into 100. That's it. Let us simplify. You get percentage of time. Always you multiply with 100. 0.4 by 1.65. If you simplify, it would be, see, let me move this point to right side. Then 40. That means I multiplied this with effectively 100. 40. 0.4 into 100 is 40 by 1.65. Let us do one thing. We can write it as 4000 by 165. Let us simplify now. 5 3 is a 15. 1 5 3 is a 15. 5 8 is a 800 is a 4000. Now 33 2s are 66. Then you get what? So maybe 32 to the 66, then you get remainder 14. Then it will become 140. Then I can use 33 3 is a 99. 33 4 is a 132. That means 24 point something you get. Okay, 24 point something, whatever. Calculation is not important. 24%. Now we will see one more question, that is D. So the question D is about DMA. We will see same question they asked about DMA transfer. Then we will see how to solve it. Now we'll see question D. Maximum percentage of time the CPU is held up for this disk IO for cycle stealing DMA transfer. So you know about, right, cycle stealing and DMA efficiency. Because of DMA, so CPU can do other work, right? Now the only thing is we are locking the bus. You know the story. In cycle stealing DMA transfer, what happens? Whenever this disk, example we are talking about disk, right? Whenever disk gets data, same story. So disk is going to first move the data from disk to device to temporary register. It takes some time. How much time it will take? 0. Already we have calculated, that is 1.25 microsecond. That means after 1.25 microseconds of time, then data will be available. Then generally in interrupt driven IO we generate interrupt. This time in cycle stealing DMA transfer, what we do is we don't disturb CPU. Rather than calling CPU, what we do is we ourselves are going to move the data from disk to main memory. For that we are going to use this data bus. Now if CPU cannot, now in cycle stealing mode only one cycle we use. That means to transfer one byte only we use data bus. After that again we give the data bus and address bus, whatever the bus, let's say bus, that bus will be given to CPU. Understand? Now I can say that CPU is held up for some particular amount of time because CPU cannot use bus at the time when we are transferring the data. It doesn't mean that CPU is completely blocked. If CPU has other instructions like addition, subtractions, okay, from other programs or from the same program, then CPU can continue, right? So that's why there is no problem. And one more justification I will tell you. You are not wasting CPU time. You are not really blocking CPU because CPU never requires main memory. Recall, in memory organization I taught you, CPU generally always takes data from cache, right? If data is not available, then it will go to main memory. At that time, if bus is not available, then only it will be really blocked. Now if hit ratio of cache is 90%, only 10% of the time your CPU will be blocked, correct? Now, so however, whatever may be the scheme, finally in the question it's not about cache and everything. So the question clearly about, we are definitely holding the CPU here, right? How much amount of time in general case is 10% if cache hit ratio is given, right? Now here cache details are not given, then what we can assume is, so whenever the DMA transfer uses this bus, then entire amount of time we assume that, let's say CPU is blocked. Here CPU is blocked means CPU cannot use this bus, okay, but it can do other works. That's a separate story. So in the problem we should understand that how much amount of time CPU is not using this bus, right? Now we'll see complete story. If you understand the process of cycle stealing DMA, then we can understand how much amount of time CPU is blocked, right? Let us see. See, this is your CPU. In the early morning, happily it is executing its instructions. Then this is your disk, okay? So this disk is very happy because it has some independent work, right? It is using now DMA. So there is no relation between, that means this DMA, this disk never takes help from CPU, right? So happily, that's why it is very happy. Now what happens is, in the early morning, whenever there is a requirement of data transfer, first of all data will be transferred to this temporary buffer, right? Already I told you. It is exactly like interrupt driven IO. So 1 byte will be transferred. How much time it will take? 1.25 microsecond we have already seen. Then now here there is a difference. If it is DMA transfer using cycle stealing, then this byte will be transferred, okay, immediately in this clock cycle. We simply block it. My dear CPU, don't use bus now. This bus is now mine. So bus will be taken by this disk, and data will be transferred through this bus to main memory, correct? Now how much time that will take, because now this disk is doing that on its own, no program, nothing, right? Maybe. So already it is given that the data transfer time, that means memory read time is 0.1 microseconds. Assume that, let's say, to transfer data from here to here, it takes 0.1 microseconds per byte. Okay, that is the memory transfer time. See the complete story. First we transfer data from this disk to temporary buffer. It takes 1.25 microsecond. After that we take the bus and we transfer the data to this main memory through hardware, I can say. That takes, let's say, 0.1 microseconds, because they have clearly mentioned that the memory read time is 0.1 microseconds. Understand? After that, that's it. Simply we inform CPU, my dear CPU, I am done, right? So, and one more thing, did you remember, already I told you when I was teaching DMA, whenever CPU actually initiates all that stuff. What is that? This, how to transfer the data and everything, like there will be, so it is not appropriate now, because I don't want to mess up, and I don't want to extend this one. I want to say that initially, generally, whenever there is a DMA transfer, we have to set up lot of registers. We have to initialize lot of disk registers. Okay, that overhead is actually called CPU overhead. At that time, CPU will execute a program. Understand? So DMA, before DMA transfer, we have to initialize lot of registers, disk registers. Okay, it's not like very simple like this idea. There will be some amount of time CPU has to spend to initialize all. That's why you remember one thing. First of all, DMA initialize transfer, CPU will initialize lot of things. That is called DMA initialization. After that, once data transfer is done, usually disk will inform. That means that DMA controller will inform CPU that, my dear CPU, please cross check if there is any error. If you have any questions or doubts related to this concept, then please go to DMA first. Okay, I already taught DMA concept. You go through it, then you understand that there is a initialization overhead which is by CPU. Then data transfer, at that time we don't consult CPU. Then after that, end of the day, once data transfer is done, again we generate an interrupt by saying that, my dear CPU, we are done. Please cross check if you have any errors. So here this overhead we have to calculate, but that is not given in the question. You see, DMA initialization and termination overhead is negligible. That is actually in the account of CPU. It's nothing but a small program. So DMA initialization is done and DMA termination is done through a software program. Okay, it's like interrupt service routine, but that time is very negligible. They clearly mentioned. Otherwise, if they give, we have to come take it. Now finally what I want to say is, in this problem, in our problem, CPU is not at all used, correct? But CPU is blocked. That is the question. How much amount of time CPU is blocked, When so if you want to understand, you should understand one thing. When are you going to use this main memory bus? This bus you are going to hold up when you are transferring the data, and the data transfer time only 0.1 microsecond, right? Only this point of time CPU got hold up, right? So finally I can say that the ratio of the time, if you see, where this memory bus is blocked is 0.1 microsecond. In overall, how much time? See, in the total story, only 0.1 microsecond is wasted. Again here also I am observing for 1 byte transfer, because for second byte transfer also same thing will be repeated, correct? So when you are transferring 1 byte in that entire story, we never disturb CPU. First we move the data from here to here, we don't disturb CPU. After that we move data from here to here, then here we are blocking the CPU, right? 0.1 microsecond. After that it will be done, then again we'll go for next byte. So that's why I can say that out of 1.25 microsecond plus 0.1 microsecond, only this 0.1 microsecond amount of time your CPU is wasted. I can't say wasted because still CPU can do other work, but it's blocked, right? But the question is about held up. Yeah, we held up the bus. That's why the amount of fraction of time is 0.1 by 1.25 plus 0.1. It would be 1.35, right? But percentage of time, if you want, multiply with 100. So it would be 0.1 into 100 is 10 by 1.35, right? If you simplify, it would be 1000 by 135. If you simplify, 527 is a 135, 5200 is a 1000. Now I can use here 27 table. 27 eights, let us try 27 eights, 8 sevens are 56, 5, it would be 216. That means it would be 27 6. 27 6, 6 7 are 42, 4 6 2 12, 16, 162, right? 162, 169, 27 sevens I will try. 7 sevens are 49, 4 7 2 is 14, 189. Yes, so 27 sevens are 189, remainder is 11, then it would become 110, then 27 fours are 108, so 7.4 percentage of time. So it was some 25% around, right? Now it is 7.4%. So very few percent of time your CPU is blocked, correct? So that is about all these questions. If you understand these questions, then most of the disk problems you can answer. See this question which is asked in GATE 2007 IT paper. Number of tracks are 500. Number of sectors per track is 100. Number of bytes per sector is 500. Time taken by the head to move from one track to adjacent track is 1 milliseconds. Fine. That means this is your, let's say, one plate. These are all the tracks. To move your read-write head from one track to another track, the time taken is 1 millisecond. Okay. So that is given. Rotational speed is 600 rotations per minute. Now what is the average time taken for transferring 250 bytes from the disk? So I don't know where is the 250 bytes, correct? So let's say this is the location. What is sector size? Number of bytes per sector 500. That means 250 bytes are nothing but half of the sector, correct? So some half of the sector we have to read. How much time it will take? So that's why we don't know where it is, correct? It depends on where it is and where your read-write head, correct? So that's why what we do is in this kind of problems, since we cannot assume that read-write head is already on top of this sector, we can't assume like that, okay? Because that's the best case, right? In the worst case, what happens? Your read-write head will be here at the first track, I can say, and the data is in the last track. That means it is very distant from your read-write head. Anything can happen. That's why what we have to do is we have to go for average case. That means we have to find out the best case and worst case, and we have to do the average. Otherwise directly you can calculate average. So what is the average here? First of all, you tell me what are the components we will have in data transfer generally if everything is given. So the main components which makes delay is seek time, correct? So seek latency. Second one, rotational latency. We have to rotate the plate, correct, to get the right sector. Then after that, once you come to the right point, we have to take care of data transfer time, correct? So it depends on the data which you are transferring. Data transfer time depends on the rotational latency, at the same time amount of data you are transferring. Let us first focus on seek time. How much seek time we have to invest to transfer this 250 bytes of data, and where it is first, okay? So this is your, let's say, plate. How many tracks we have? See, this is your problem. This is a plate. Number of tracks are 500. You have track 1, track 2, track 3, track 4. In that way, there are 500 tracks. This is 500th track. This is first track. Now it is almost, your read-write head is almost near to the first track. Okay. Assume that, let's say, it is on top of the first track. Now if your data is also available on the same track, there will not be any seek latency, correct? Because nothing, I mean, you don't need to move it, right? In the worst case, we have to move like this 500 units, because then only you get 500th track. Now you see, to move your read-write head just to one track, it takes 1 millisecond because the time taken by the head to move from one track to adjacent track is 1 millisecond. If you have 500 tracks, then almost 500 milliseconds of time you get to go to the innermost track. For outermost track, zero delay, right? Zero delay. Because already I can say that your IO head is available at just right away. Okay. So 500 is the worst case, 0 is the best case. So average what I can do is, so I can assume that let's say your data is available at 250th track. So that to go to that 250th track, it takes 250 milliseconds approximately. One more or less doesn't matter, correct? So let us assume that 250 milliseconds is seek time. So here we are computing average seek time, right? Not exact seek time, because you don't know exact seek time. So average seek time is nothing but maximum seek time by 2, right? What is the maximum seek time? 500 milliseconds. I am taking half, 250 milliseconds. That would be the idea. Now rotational latency. Once your read write head comes to the right track, then see, this is the track. Now we reach the track. Where is the data then? Data can be here or here or here, anywhere. Then in the average case, it takes half rotational latency, correct? That means average rotational latency here we have to take. Finally, in one line I can say average seek time plus average rotational latency plus data transfer time. Data transfer time, we have exact answer because we have exact calculations, because we know how much amount of data you are transferring, right? Not a problem. So average rotational latency, if you want to know, first you should know rotational latency. What is rotational latency? Is it given? No, but rotational speed is given. With that we can find out 600 rotations for 60 seconds. One rotation, by this time you might have got experience, right? So it would be 1 by 600 into 60 seconds, right? So it would be 60 tens, then it is 1 by 10 seconds. If I write into milliseconds, it would be 1000, because everything is in milliseconds, you see. 1000 by 10 milliseconds. It would be 100 milliseconds, remember it. So finally, rotational latency is 100 millisecond. That means one rotation time is 100 millisecond. Then average rotational latency is nothing but half of the one rotational latency. That's why it is 1000 by 2, which is nothing but 500 milliseconds, correct? Let us cross check whether we are right or not. Not 500, it is 50, I think. Let me, that's why I compute it again. So 600 rotations per 60 seconds. One rotation dash time, it would be 1 by 600 into 60, which would be 1 by 10 seconds. That means 1000 by 10 milliseconds. It would be 100 millisecond, correct? 100. Then half is 50 milliseconds. Right, 50 millisecond here. 250 millisecond is for average seek time. Now data transfer time. Again, data transfer time depends on amount of data and rotational speed. What is the amount of time data you are transferring? You are transferring, I think, what is the average time taken for transferring 250 bytes. So let us calculate time required to transfer the data. Simple. This is, now we are at right place. Okay, let's say you are at right place. This is the data, 250 bytes. To read it, plate has to be rotated again. How long? Exactly equivalent to, this much, right? What is this length? We don't know, right? But I have an idea. So if you want to read entire track, one rotation is required, correct? What is track capacity? That's why track capacity is important. So track capacity, if you see in a track, how many sectors we have? 100 sectors. So I'm calculating first of all track capacity, 100 into each sector has how much space. See, number of bytes per sector is 500. So 100 into 500 bytes you have in a track. This track contains this much data. Now let me ask one question. If you really rotate your plate fully, how much time it will take? 100 milliseconds. So that means to read this much amount of data, only one plate rotation is required, that is 100 milliseconds. But so I can write like this: within 100 milliseconds I can read 100 into 500 bytes. Am I right? Yes. But do you have this much amount of data? No. If I had this much amount of data, answer is 100 milliseconds. But data transfer time here is only 250 byte transfer time. So these many bytes takes this much time, then 250 bytes requires how much time for your plate to rotate. So it would be 250 by 100 into 500. You know the formula, right? It is direct proportionate. Then reverse it. 250 by 100 into 500 into 100 milliseconds. Answer will be in milliseconds. So see, I think this 0 will become 1000. 251s are 254s are, right? You get 4. Now 4 into 50, 200. So 100 milliseconds by 200 milliseconds, right? It would be negligible definitely. So if I simplify it, you get 1 by 2, that means 0.5. So it would be 0.5 milliseconds, isn't it? So here let me simplify it again, very simple. 250 bytes by 100 into 500 bytes, correct, into 100 milliseconds. So answer is in milliseconds, remember, see, milliseconds. Now remaining part you simplify. So bytes will be cancelled, then 251s are 252s are, right? 100 will be cancelled, 1 by 2. 0.5 milliseconds I got. So very negligible time, of course. Then let us simplify. 250 for seek time, 50 per rotational latency, average rotational latency, plus 0.5 for data transfer. It would be 300.5. 300.5. So option A is the right choice. In that way, so very confidently we can answer the questions. It's not a big deal. Okay. Now there are some other questions. You try to answer them on your own. If you cannot, please post on the website. Okay.